Man, I'm sure I'm happy that after a month of work I finished writing that physics engine I told my calc teacher I was gonna make. What do you mean I need to make a 15-minute video? And it's due by the end of the week. Alright, let's go back to the beginning for some context. So, about a month ago, I had finished my semester on multivariable calculus. Or at least, I had been taught all the actual material. That said, I had to do some kind of final project, which could have been anything, as long as I was doing multiverse stuff. So, what that meant was, I could have made a review game to keep all the stuff I had just learned in my head. I could have made a funny music video parody with my friends. But, no. I decided to be extra, because of course I did. I proposed to my teacher to program a physics engine, and produce this video. Just to make sure everyone's on the same page, a physics engine is any kind of computer software designed to simulate physics. So, given some objects, it'll tell you where they go and how they should interact. They're really useful tools. You'll see them all the time used for applications like animation, games, making sure your card doesn't implode on itself. So there's also a lot of different kinds of things you can simulate with a physics engine, or make a physics engine for. For instance, Sebastian Lake has made some really great videos on making a fluid simulation. I'm not Sebastian Lake. I will not be doing fluid simulation today. Instead, what I made is just a rigid body simulation, meaning that all the objects are completely solid. There's no objects that are going to bend or break or anything. More specifically, I'm just using 2D polygons because 3D is a whole other can of worms on top of the core physics engine stuff I'm writing. And also I only had a month, so... Basically, although there's multiple sources I went through, my goal was to get to something like this. This website is myphysicslab.com, which provides a lot of information about the inner mechanics of a physics engine for free. It's probably the number one resource I would recommend you look at if you were to start researching this yourself. But in short, if I could get to a point where I have a bunch of objects and add some forces to them and let them bounce around, I'd be happy. For this project, I chose to write in Java using the Abstract Window Toolkit library, or AWT. This is just to handle the low-level stuff like getting a window open on screen and drawing some basic shapes. Is this the best way to create a real-time application? Probably not. AWT is built first and foremost to build like basic GUIs, but either way, we can make it. So that's enough rambling for now. Let's get to the actual programming. Getting started, I defined some class to hold the data I'd be needing throughout the program. I made my own rudimentary vector class. It just holds two variables, x and y, and has a big list of whatever vector operations I'd end up needing. I'm very thankful I made this early because there's a lot of places I'd end up needing either vectors or vector math. Next, I'd make a class to define the properties inherent to a physics object. That, in this case, would be like the mass, shape, center of mass, and the inertia. Mass and shape aren't that bad. Mass is just a number, and shape can be defined as a list of vectors that we're going to treat as points going counterclockwise. I totally didn't mess up and list the point as clockwise until the very end of the project. Like, I don't know what you're talking about. I fixed it eventually. Anyways, we're just going to be given mass and the shape, and we're just going to copy them over. As for the center of mass and inertia though, we're going to have to calculate those. As a reminder, to find the center of mass of an object, what we want to do is we want to take the average position of every tiny bit of mass in the object. The way we do this is by multiplying the position at a point by the mass at that point, and then dividing by the total mass. The problem is that we don't have a list of points. We have a polygon. So here's a situation where, as a programmer, you have to ask yourself, can you just estimate the solution, or should you actually sit down and find a definitive answer? Here, you could try to estimate the center of mass by getting a massive list of points inside the polygon, but this is a really inefficient process. For each x-coordinate, you have to check a massive list of y-coordinates, and for a decent estimate, we could easily be doing thousands of operations. So our other option is, does anyone hear boss music? Oh, multivar! What we have here is an example polygon and the center of mass equation written in terms of calc-free. To break this down a little bit, A is the area of the polygon, and mx and my are respectively the double integral of x over the region and the double integral of y over the region. And essentially, these double integrals up here are equivalent to that weighted sum of mass times position plus mass times position plus mass times position, so on and on. And the area is equivalent to the total mass from before. The reason we can simplify it down to this is that for my simulation, I have assumed that mass is evenly distributed across the entire area. So there's not more mass on one side than the other. Like a square inch over here is the same weight as a square inch over here. Okay, so this is neat and all that we have this and we can describe it mathematically, but that isn't a step-by-step solution that we can just feed into Java. What we need to do is we need to break this down somehow. Let's start with area. Now, there's multiple ways you can get to a formula for the area of arbitrary polygon. For here, I'm going to highlight a neat hybrid approach between like a little bit of linear algebra stuff and a little bit of geometry. So recall that if you have two vectors, such as going from origin to one point on the polygon to from the origin to another point of the polygon, you can take the determinant, and this determinant is actually the area of this parallelogram here, except the parallelogram, except it returns the negative area if you're going in clockwise, and it returns the positive area if you're going counterclockwise. So this might not look very useful at first glance, but what we can do is that we can divide by half. And okay, this might all still not look very useful at first glance, but if we go in order or counterclockwise of the points here, and we take the determinant of each new pair of vectors that are next to each other and represent these points coming from the origin to a point on the polygon, what we can see is that as we go along, this negative area starts getting canceled out by a positive area going the other way, and leaving some extra positive area over here, and this cancels out to 0. And then if we ever go backwards, it cancels out the positive area here and brings back some negative area here. And then we go all the way over again, and this is counterclockwise, so it's positive area again. And so this cancels this out to 0, this cancels the stuff down here out to 0, and brings this back to positive. And what we see is that eventually we just get the area of only the polygon. Also, this is why before I said that the points were listed counterclockwise. It's to make this work out well. Oh, it'd be negative otherwise. But in short, this is one way you can figure out a solution to the area of a polygon. It's half the sum of all these determinants. And I hope you can trust me, even though these drawings are very sketchy, that because it's a closed curve, the movement that gives you a little area outside, or double counts, is eventually canceled out by error going the other way. And also, you might realize if you've taken some competitive math or know your geometry really well that this is the shoelace formula. This is one way you can verify the shoelace formula, with that little trick where you line up the x and y coordinates and do this multiplication and subtraction thing. That's where this comes from, or at least one way to verify it. This is nice, but eventually I don't know of a clean geometric way to interpret these integrals the same way. So we need something to take us from a double integral to the sum of some factor that we can, something that we can easily compute. And more importantly, this is some finite sum. But luckily, I'm in Calc 3, so I know a solution for this, and that's Green's theorem. What Green's theorem says is that if you have a double integral and you can separate the inside into the partial derivative of m with respect to x and the partial derivative of some L with respect to y, you can actually turn it from a double integral, which goes over the entire region, to a path integral, which goes along the outside of the region. This might seem like it comes out of nowhere, but it's actually the perfect thing for this. Since now we can take one of these double integrals we had before, like mx, that was the double integral of x over the region, and if we see, okay, x can be the partial derivative of m with respect to x, which would give us m equals x squared divided by 2, and then there's no y term in here, so then we can just say partial derivative of L in terms of y is 0, L of x and y is 0, and using this we can get Green's theorem to convert us from a double integral over the entire region to a path integral of 1/2 x squared or dy. We do need to make a short detour to talk about how we mathematically represent and going down a line. And a simple way we can do this, although there's many ways, is to use what's called a linear interpolation, or a lerp. This function will give you x1 if t is 0, and it'll give you x2 if t is 1, because this cancels out. And then anywhere in between, so if it's like 20, if t is like 0.2, that'll give you 20% of the way from x1 to x2. And this works for y as well. In essence, this is how you can represent and all the points in a line segment. You can have this parametric system and then have t go from 0 to 1. So if we have our equation for lerping between 2 points, what we can do is apply that to each of the segments in order to mathematically describe our path. So here xi is x at index I, xi plus 1, or xi plus is the next one in the loop. Using this, what we can do is that we can take our double integral, which we've turned into a single line integral, and then substituting in our lerp equation for x and y, and we can arrive here with some u substitution and find that this line integral is equal to the sum of a bunch of integrals going from here to here to here to here to here and back, which is fantastic because this is something we can work with. We still need to do some regular calculus as to break down this integral into something nicer, but after some expanding and simplifying, there's this neat trick here where these terms actually cancel out when we're adding them all together in a loop, because eventually you cover all the different indexes. We get an equation like this, which is very simple and does work in a way where I can just tell the program, hey, this is a finite sum of these values. I can tell a computer program to do that. And in fact, we can do this for area, we can do this for the x component we needed earlier and the y component we needed earlier that we needed to divide by area to get the center mass. So we can do center mass. And we can do the same thing for inertia, although I'm not showing it here, but it's much the same process of setting up this double integral, changing it to a line integral, reasoning about how a polygon works, and then finally transferring it to a very nice simple sum of a bunch of terms. Here's what that looks like in code with the update center mass function and going through the entire list of points in the polygon on getting the current and next points in the list, and then using those linear algebra functions that I defined earlier. Excuse my terrible naming of variables. At the end here, we change. The way I've implemented this is that it will change the center of mass so that it's centered at 0, 0, and then update inertia works much the same way, using also going through the entire list and doing a similar calculation and setting it at the end of the function. You may have noticed that took me way too long to explain, so we're going to blitz through some other changes. Yeah, we still haven't gotten to the actual physics sim of the physics simulation. And so all I have so far is a bunch of numbers and some code that draws to the screen. Great. Let's go through this real quick. Now let's go back to an example by my physics lab. Here with just two objects, we can tell that there's a lot of forces going on. There's spring forces is going in every which direction. There's gravity going down, and there's some damping force that's acting as a stand-in for friction or air resistance or whatnot. If we go down, what we can see is that what we're really looking for is a solution to a differential equation. The forces added together, this is some spring force, there's gravity, some damping factor. All these forces combined give us the acceleration we want. However, this is where things get complicated. And so the forces give us acceleration, which is how much velocity should be changing. I mean, velocity gives us how much the position should be changing, including rotational position and rotational velocity. But if you take a look at something like springs, that force is dependent on the position of the objects. So we have ourselves bona fide differential equations. So we're in another one of those situations where, as a programmer, we have to decide whether or not we're going to sit down and figure out the mathematically perfect solution, or we're going to just do it numerically, just have an estimate. I could tell you that we're going to solve these equations, but I'd be lying to you. Not only is that differential equations is the primary focus of Calc 4 and I'm in Calc 3, but also differential equations range from annoying to the free body problem famously has no closed form solution, and we're dealing with physics simulations with potentially many more objects and many more complicated forces than that. So we're just going to estimate. So there's a bunch of different ways you can take some differential equations and estimate how the system progresses. My physics lab uses something called the Ridge-Crudo method, which is basically a clever way of taking a few new samples and getting your estimate out of it. I ended up just using what's called semi-implicit Euler, or just basically just a version of Euler's method, which sounds fancy and all, but it's literally just we're going to take acceleration and multiply it by the amount of time that has passed and change the velocity by that, and then we're going to take velocity, multiply it by the amount of time that has passed, and add it to position. And same thing for the rotational equivalence. You might wonder if that is less accurate, and theoretically is. In practice, our time steps are so small, and for our purposes, it's about as accurate as we need it to be anyway. So, with a bunch of other code added together, we can also add in some strings, and that gets us something similar to what the simulation before had, which is a bunch of objects moving around, but they're not colliding yet. We need to do collision still. And that's what took me 3 weeks of work. But in order to handle collisions, we need to talk about time travel. Call me Doctor Who, because no one's going to remember my name when I die. What a stupid joke. Consider these two frames. One is a list of the objects as we had them on the previous frame, and other is a list of the objects as they will be on this frame. Our program already has the capacity to change the object's positions and rotations depending on what forces and velocities they already had. However, right now you can see that on the after frame, the objects have collided. So how do we resolve this? Well, what we're going to do is on the after frame, we're going to check for any collisions between objects, and we're going to, for each one of them, we're going to figure out when those objects collided. Now, we don't have any kind of mathematical solution for this. It's a little bit brute force. What we're going to do is we're going to take these two objects as they were on the previous frame, and we're going to step forward halfway. If it's colliding, then we know we stepped too far and we go halfway closer. If it's not colliding, we know that it's not long enough yet, so we go back and forth until we're precise enough that we basically got it. So once we know that this is about where the objects have collided, my program prefers it so that they're slightly not touching instead of slightly intersecting. Then what we do is then from here we can apply the changes to velocity that will occur here due to a collision, and then have them continue to simulate back to the end time. If you're wondering how we can programmatically determine if two polygons are colliding or not, what we can do is use something like point polygon. So if a point is inside the polygon, then a ray going from outside to inside to the point will collide an odd number of times. If it's outside, it'll be an even number of times. From there, you can check if the line segments intersect. You can either do this very efficiently with something like a sweep line algorithm, or you can be inefficient and just brute force everything. So now, as you can see here, this can cause other collisions to happen, so we're going to keep checking to see if there's any collisions between two new pairs of objects, and then add that to a queue to check up on. So for these two, then the same process happens. We back up, but now we're going from this intermediate step to step forward and check, and we're going from the last known data, and that was going to step forward and see they collide about here, and then those are going to collide, and this goes on and on and on until we sort out every collision. Anyways, this is the draw the rest of the owl part of the video, where I skip over 3 weeks of delirious bug fixing and actually implementing that and terrible code. But after all is said and done, that was actually my reaction at 1 a.m. when I got that working. Although I did have to go back and bug fix some more things, but after a few fine-tuning adjustments, it looks something like this. We get realistic, believable collisions between all of the blocks. Although you might notice some clipping here and there, that's kind of because I've only implemented one kind of collision. There's more features to make an engine like this more stable, but yeah, I don't know, pretty neat, I think.